All right, chapter 23, three circuits problems. Problems number 26 and 29 are basically VIRP charts. The textbook does not ask you to do your power column. I'm going to fill that in just to kind of reinforce how to do it and how to use it as a check for the whole circuit. 31's a little different. We'll get to that obviously at the end, but 26 and 29 are basically VIRP charts. For problem number 26, my circuit looks slightly different than the way the textbook drew it. In the textbook, this 5 ohm resistor is drawn up here, right on the top. It doesn't really matter where you put it because this 5 and this 5 are in series. I think it's easier to put them right here because it becomes a little more obvious that they're in series. But leaving it up at the top would be no different as long as you recognize that this 5 and this 5 are in series. If we were going to redraw this circuit, we could make it simpler by combining some resistors. If we trace the path coming out of the battery, we would recognize that we have to go through this 5 ohm resistor first. Then when we get here, there's a choice. We could go through this branch, which has 10 ohms of resistance, or we could go through this branch, which has the two 5s, which actually also is 10 ohms of resistance. So these two parallel branches are equal. So redrawing it one way, we could go battery, 5 ohm, resistor, and then 10 ohms, and we can make the other branch 10 ohms because again, two 5s in series make a 10. Get back to the battery. We could combine the two 10s in parallel over here, so we could have our battery, our 5 ohm resistor, and a 10 and a 10 in parallel. 1/10 plus 1/10 makes 2/10. 1 over that is 10 over 2, so these two 10s are equivalent to a 5. So I could draw it as a 5 here. And then I've got two 5s in series. So the circuit comes down to 10 ohms of total equivalent resistance. This 10 by itself is equivalent to this whole combination up here. That means my total resistance for the whole circuit is 10 ohms, and my total voltage for the whole circuit is 10 volts. So if we do Ohm's law for the whole circuit, 10 volts equals I times 10 ohms, the total current is 1 amp. Next step in a VIRP chart, are there any resistors in our circuit that actually get that total current? And in our case, yes, there is. There is one resistor that happens before any splits, which would be this 5 ohm up here. So that first 5 ohm resistor will get 1 amp. If we had any resistors down here after the two branches come back together, it would also get our 1 amp. Because I have a resistance and a current for that particular resistor, I can find its voltage drop, or its voltage difference, or its potential difference. They all mean the same thing. The textbook uses the phrase potential difference, but it's just how many volts are used on that resistor, which again is 5 volts. I had 10 volts total. I've used 5 up here. That means I've got 5 left for the rest of my circuit. And if I look at the two branches, this one has only one resistor, this 10 ohm branch. So it has to use all of the remaining 5 volts on its own. This branch has two resistors, so between those two resistors, you'll use a total of 5 volts. So there's two possible loops you could take, and again, either loop has to use all 10 volts. The first loop is start at the battery, go through this, and you would have 5 volts used here, 5 volts used here, get back to the battery. The other loop is start at the battery, go through this resistor, then go through both of these. And again, when you complete either of those loops, all 10 volts have to be used up. I can find the current here because again, once I know 2 out of the 3 first columns, I can find the third one using Ohm's law. So V equals IR for just that resistor. I know 5 volts is going to equal my current times my resistance, which is 10 ohms. 5 over 10 is just a half, so half an amp goes that way. If 1 amp went into this split and I know half an amp went this way, well, how much current is left to go this way? The other half of an amp. These two currents coming out of a split will always equal the current going in. In this particular circuit, it's a 50-50 split because my two branches are the same in terms of equivalent resistance. They both have 10 ohms of resistance, so they will share the current equally. If I had a circuit where one branch had more resistance than the other, the current would not split equally, but it would always add up to what went in. Since these two resistors are in series, they will both get that half of an amp. I can now do Ohm's law to figure out the voltage. And again, it's just going to be I times R, so 0.5 times 5 is 2.5 volts for each resistor. And I can double check 2.5 on this one, 2.5 on this one, gives me a total of 5 volts, which is what I said I should have on that branch before. Now I can just very quickly fill out the power column. That's just I times V. Power is I times V. It's also got two other forms, but I times V is the easiest form, no fractions. So 5 times 1 tells me 5 watts used on that first resistor. 5 times 0.5 tells me 2.5 watts used on this resistor. 2.5 times 0.5 is 1.25 watts. 2.5 times 0.5 again is 1.25 watts. Add all those powers up. 5 plus 2.5 plus 1.25 plus 1.25 adds up to 10 watts. Go back and check total voltage times total current to get total power. 10 times 1 is 10. We agree we did this VIRP chart correctly. Let's move on to number 29, a very complicated looking circuit the first time you look at it. If we're careful about rechecking and retracing our current paths, we can redraw this in a lot more simple fashion. We come out of this battery and we're starting at the positive terminal, the longer line. We have to go through the 3 ohm resistor. We have no choice, no splits. But then we get here, this point, and we have a couple different ways we could go. If we go through the 4 ohm resistor, we could get back to the battery without going through anything else. If we go through the 48 ohm resistor, we could get back to the battery without going through anything else, just wires. And if we go through the 16 ohm resistor, again, we could get back to the battery without going through anything else. That means that this 4, this 48, and this 16 are all in parallel because you could go through one but not anything else and get back to the same point. So I redrew the circuit down here and it looks totally different, but these two are equivalent because again, starting at the battery, I must go through the 3 ohm, but then I have a choice of going through the 4, the 48, or the 16, and then getting back to the battery without going through anything else. So being able to trace the path of the current starting at the battery and getting back to the battery and redrawing the circuit as something simpler is a really, really useful skill to have. Again, for the VIRP chart, which is what I'm being asked for here, the voltage and the current, I'm going to also do the power and double check it. But to do that, I've got to start by finding the total resistance. So this 3 by itself I'll leave, and then I've got the 4, the 48, and the 16 in parallel, so I'm going to start by combining those. 1 over 4 plus 1 over 48 plus 1 over 16. And that would equal 1 over the equivalent resistance. I'm just going to use my calculator for that rather than worrying about fractions or any of that. So I'm going to go 1 over 4 plus 1 over 48 plus 1 over 16. Not that these would be that hard to combine. You could go to 48s pretty easily. And then 1 over that is, of course, 3. So this whole branch acts like a 3 ohm resistor. So if I redrew my circuit again, I'm going to go up here this time. I would have my 12 volt battery. I'd have a 3 ohm resistor. And putting a 3 ohm resistor here is equivalent to this whole combination. And then I'd go back. So 2 3s in series. My total resistance for the whole circuit is just 6 ohms. My total voltage is 12 volts. So if I do V equals IR for the whole circuit, 12 volts and 6 ohms, my total current is 2 amps. Do any resistors actually get 2 amps? Yes, this one. There are no splits. Whichever version of this I look at, I go from the battery directly to the 3 ohm and there's no splits before I get to that 3 ohm. So that first 3 ohm resistor gets all 2 amps. How many volts does it use? In other words, what's the potential difference across it? Well, I'm going to do Ohm's law again, but this time just for that resistor. 2 amps of current, 3 ohms of resistance, 2 times 3 is 6, so it uses 6 volts. How many volts are left? I put 12 into my circuit. I've used 6 volts up here. How much is left for the rest of this? 6 volts. Again, I've got a circuit kind of like the first one, where the parallel branch had equal resistance, so the voltage is going to kind of split 50-50. But the correct way to think about it is how much was put in, how much was used, how much is remaining, and in this case 6 volts is remaining. As I complete my circuit, I'm only going to go through one of these three possible paths. So whichever one I go through must use up the 6 volts that are left. So they're all going to get 6 volts, right? Things that are in parallel get the same voltage drop. So this is a case where, again, I'm not just going to add these. I don't want to add 6 4 times to get 24. I have to think which resistors am I going through. 12 in through this one and this one, 12 volts used. Through the 3 and the 48, 12 volts used. Through the 3 and the 16, 12 volts used. Now that I have 2 out of 3 filled out, I'm just going to use Ohm's law to find out the current. V equals IR, so current is V over R, and I'm just going to do that for each row. I'm going to do the voltage divided by the current. So here I would have 6 over 4, which is 2/3 of an amp. Here I would have 6 over 48. 6 over 48 is 1/8 of an amp. And I could write these as decimals if I want. 6 over 16 is 3/8 of an amp. So if I add these up, am I missing some current here? Did I make a mistake? Because I put 2 amps coming into this junction. If I add these up, that's half and that's 2/3. I'm sorry, that's not 2/3. This is 3/2. 1.5 amps right here. I flip that in my head, and that makes more sense because if I have 2 amps coming in, I've got 3/2 or 1.5 amps going this way. 3 over 2. I've got 1/8 of an amp going this way. 3/8 going that way. That adds up. 2 going in splits into 3/2, 1/8, 3/8. And these all add up to the 2 amps total that I have. So 3/2, not 2/3, 3/2 of an amp there. What I would need to do at this point to double check that I have done this correctly is just multiply across. So I times V gets me power. 6 times 2 is 12. 12 watts used on that first resistor. 6 times 3/2. So 6 times 1.5 would be 9 watts. 6 times 1/8, that's 6 over 8, or 3/4 of a watt, or 0.75 watts. And then 6 times 3/8 would be 18 over 8, so let's just get that as a decimal quickly. 18 over 8 is 2.25 watts. So if I add all of these up, that's 3, 9, 24 watts total. Go back and double check. 12 times 2, total voltage, total current, is that 24? Yes, it is. So we did our VIRP chart correctly again. Let's switch over to number 31. So in problem 31, things are a little bit different. I'm not really being asked to do a VIRP chart here. What I really have to focus on is the rules for how current and voltage works together in a circuit. So I've got a circuit set up where I kind of similar to the last one, I have to go through this first resistor, this 10 ohm resistor. And then it looks like I have a parallel split where I've got 2 equal branches, each with the same resistance R that we don't know. I've got a switch so I can open and close this branch. I essentially get rid of this branch, or I can have it connected. And then I also don't know the battery. This kind of rounded off E, again, stands for EMF. It just means voltage. So I just don't know the battery voltage, and I don't know these 2 resistors. The other thing it tells me is that when I close the switch, essentially when I include this branch, my current goes up by 50%. So if the original current without that branch, with that branch closed off because the switch is opened, if that current is I, when I include that branch, my current will be 1.5 I. So the key to this one is to look at the 2 loops and the 2 possibilities here. And keep in mind that whatever voltage I put in, even though I don't know it, whatever amount of voltage I put in with my power supply or my battery, I've got to use up as I go around the loop. So I'm going to draw it as 2 separate circuits. When the switch is open, I've got the battery, I've got the 10 ohm resistor, and I've got that 1 resistor R. Because when the switch is open, this branch is broken. There's no complete path to get from here to there, so it essentially disappears. Might as well not be there. When the switch is closed, that branch is connected. I go from my battery to the 10 ohm resistor, and then I have a parallel split between two identical branches. And then I go back to the battery. Two of the same resistors in parallel, I'd have R over 2, I would have 1 over R plus 1 over R is 2 over R, so my equivalent is R over 2. It would be the equivalent of half of 1 by itself. So this circuit is the same as battery, 10 ohm resistor, and then a resistor of 1/2 R. And that just simplifies it a little bit. It's going to be a little easier to look at this version rather than that version. Let's take a look at this first circuit now. In this circuit, I'm putting some unknown amount of voltage in. So I'm going to use that kind of squiggly E for EMF as my variable. That's the voltage I put in. And then the voltage I use here and the voltage I use here have to add up to that. Well, how do I find out how much voltage I use on a resistor? Well, I use Ohm's law. The voltage on that resistor is the current times its resistance. I don't know the current, so I'm just going to leave it as I. I do know that resistor, so I times 10 is using Ohm's law to find out how much voltage gets used on that first resistor. The second resistor gets the same current because it's in series, and I don't know the resistance either, so that's just R. If I want, I can pull the I out, so the voltage in would equal I times 10 plus R for this loop with the switch open. With the switch closed, and again looking at my simplified version of the circuit, rather than two R's in parallel, just a single R over 2, I'm going to put the same voltage in. I'm going to use voltage on these two, and again they combined have to use up the same amount of voltage that was put in. But the textbook tells me that the current in this circuit is 50% bigger than the current in this circuit. So the current in this circuit is 1.5 I. If this one was I, this one is 1.5 I. So I'm going to have 1.5 I times 10. And then I'm going to have 1.5 I times R over 2. So let's see if we could clean that up a little bit. I'm going to go pull my current out of this. So I would have, well actually let me do a little cleanup before I pull the current out. This would be 15 times I. And then this would be 3/2 times I times R over 2. So this would be 3/4 times I times R. All right, so 3/2 instead of 1.5. The 2 and the 2 in the denominator make a 4. So 3/4 times I times R. So now I'm going to pull the current out. I'm going to have I times 15 plus 3/4 R. It's the same voltage, so these sides need to be equal to each other. So combining these, I'd have I times 10 plus R equals I times 15 plus 3/4 R. I can cancel out the I's, which is why I pulled them out. So 10 plus R has to equal 15 plus 3/4 R. Combine like terms, I'm going to move the 3/4 R over here by subtracting. I'm going to move the 10 over here by subtracting. 1/4 R has to equal 5. Multiply both sides by 4. The resistance is 20 ohms. If I needed to go back and figure out the battery voltage, I would have to know what the current was, but just to find the resistance, I've got enough information, 20 ohms.